So in this part, we are going to talk about integrated rate law. In the previous slides, we saw how to calculate, how to find out rate law by using the initial rate. So we do different sets of experiments, changing the concentration of the reactants to find the ratio, to find the rate, reaction rate, and as a result, by comparing the rate with the given set of experimental condition, we can determine the reaction order A, B, C, and then also reaction constant K. Here we have a different approach. We have now integration of the reaction rate, and this one is called integrated rate law method. So integrated rate law gives the concentration reactants or products at any time after the start of the reaction. This is a difference compared to the initial rate law. Initial rate law only concerned about the initial rate, but integrated rate law, we can calculate the concentration at any time with the start of the reaction. So the reaction order can be 0, 1, 2, sometimes 1/2, sometimes 3/2, 1/2, and sometimes -1. But many cases, most of the cases, the reaction order is either 0 or 1. This one is most frequent, and second frequent is the second order. So we're going to focus these three cases to find integrated rate law. So when you monitor, so this is for generic equation, A is a reactant. So A is now going to react to form the product, and then A is now consumed in over time. So when you monitor the concentration of A as a function of time, it is always decreasing. So initially we put one molarity of A, then it is decreasing either linearly or exponentially decreasing or more rapidly decreasing. This is a typical example of a zero order reaction. Exponential decrease is now corresponding to first order reaction, and more rapid decrease is now corresponding to second order. So zero order rate is represented as just constant A. This is independent. The rate is independent of concentration A. First order rate is now rate constant times A to the first power, and second order rate is now K times A to the square. Let's see individually case 1, case 2, case 3. I put this one in bold because this one is now, we see this one more frequently, more than zero order reaction. Let's see zero order reaction first. Rate is now just K. So rate is negative dA over dt. Rate is instantaneous rate. As you saw before, this one is represented as negative dA. D, the molarity of A over dt. And this is a constant. When you use integration on both sides, then we find that A is just constant, constantly decreasing as a function of time with y-intercept A sub 0, which is initial concentration. As you saw here, this is initial concentration. It is now constantly decreasing linearly. The slope is now the reaction constant, negative K. And then when you measure the slope, we can find out the reaction constant K here. Second case is now we see most frequently in the rate law, which is the first order. Rate is now K times A molarity of A. In this case, we find it is always exponentially decreasing. When you substitute rate as instantaneous rate, which is negative dA over dt, which is K times A, then when you solve this one and integrate it, this is basically differential equation. Very simple first order differential equation. When you solve it, then you find A is now exponential function as a function of time. So exponential negative kt. The initial value is now A sub 0, which is initial concentration. So when you draw this graph of A as a function of time, so concentration as a function of time, with K value, different values. K is now 0.1, smaller 0.05, 0.03, 0.01. They all follow the exponential decreasing profile, but more rapidly when K is now higher. So A is now decreasing more rapidly when K is higher. A is now decreasing less rapidly, slowly when k is smaller. As you see, the profile as the k is now larger. Anyway, what we need to remember is now A is following the exponential decreasing profile when the reaction order is 1. So always, first order, the concentration of reactant A is now initial concentration multiplied by exponential factor, exponential negative kT. We always want to put this one into a linear formation. So let's take natural log, because we have exponential here, take a natural log on both hand sides. Then this one is now transformed into this equation. This is the same equation. Natural log A is equal to exponential is coming out. Negative kT plus this becomes also natural log of initial concentration. So y is equal to mx plus b form. So when you put this one, natural log of A concentration as a function of time, then natural log A on the y-axis, time on the x-axis, we find is linear relationship. We have like several data points here that will follow linear relationship. When you find the slope should be negative k, negative rate constant. The y-axis, y-intercept is now natural log of initial concentration of A. So when this kind of graph, when you can draw, always find the slope. The slope is now negative k. Third relationship is now second order rate. Rate is now k times a square. So in this case, the concentration A is now, slope is now most rapidly decreasing. The slope is instantaneous rate, most rapidly decreasing, because now as the A is not decreasing, rate is more rapidly decreasing, because this one is now like second order square, proportional to square of A. So when you put rate as dA over dt and solve this differential equation, we find this relationship. 1 over A is equal to kT times 1 over A sub 0. So when you plot 1 over A is reciprocal of A as a function of time. So time is on the x-axis, 1 over A is our y-axis. Then when you have a linear relationship, linear regression of the data, we find a linearized data. The slope of this line should be k. So when you draw the graph as a function of 1 over A over time, then the slope is now the reaction constant k.